Hello, this video is entitled Vector Valued Functions. Now earlier in this textbook, something you would likely have seen in Cal 2 near the end of the course, unless perhaps your instructor ran out of time for whatever reasons, but you can define a plane curve x and y in terms of parameter t. So they were called parametric equations, where instead of saying y is a function of x, you're saying that x equals a function of t and y f of t, and then y would be g of t. So each values of t then would give you the appropriate xy coordinates. Now you don't have to be concerned, at least in my class, as far as having to really graph these, especially when we talk about space curves here in a minute. But I'll just show you this real quick when this calculator warms up. That you can put the calculator in parametric mode, and then when you use the same function you would normally equal y equal, it's going to bring up this pair of equations right here, and then the variable that you normally use that represents x then will be t automatically when you put it in there. And we talk about the arrow represents the orientation of the direction of the curve as t increases. So sometimes it's important that the direction of the curve. Right, so let me clear this out and just show you. I go to mode, and then there normally we leave it in function mode, but here if you put it in parametric mode and you go y equals, or that, see they're pairs. They have to be done as pairs. And then, like I said, if you want to enter like x, so 2 and this, or you want to enter a t, use the same button you would to enter x, just like that. So now, unfortunately, these only work for plane curves, since we're now, in the world of 3 dimensions at times. The graphing calculator can't do that. Who knows? Somewhere down the road, they might be able to. You might be watching this video many years from now, and they'll be able to. But that's okay. You're not going to be made to graph them. So now we have what's called a vector valued function, which actually accomplishes 2 things. It's representing a point on the graph and also a vector stemming from that point. So now they're written in standard unit vector form. So it's saying r of t, r is a vector, it's got a bold face there, is whatever f of t with I plus g of t with j. And then space, we add h of t, so it's 3 components. So f, g, and h are real valued functions of the parameter t. And of course there it is in component form, which is what I usually prefer. And like I said, you're not going to have to be responsible for doing this in my class by any means, and hopefully no one would make you. But here's a curve where it's the f of t here is sine of t, g of t is cosine of t, and h of t is just t, and it goes from t equals 0 to 6 pi. And look at that little spiral. Looks like an old slinky toy. I think it's called a helix or something like that. So it just keeps spiraling upward like that. So that's pretty neat. So we just plot points all along there, even though it is a vector valued function. Let's see. Now, vector valued functions, we have to be careful, see if there's any domain issues. And to find the domain of a vector valued function, it has to be the values of t, which that's what domain is for t. That would be common to all component functions. So in other words, if any one value doesn't satisfy one part of the component function, then it can't be used anywhere. So we're looking for the usual stuff. Divide by 0 is no good. Negative under a radical. Logarithms, more specifically the natural log, you have to take only positive quantities. So here we have, so for natural log of t, that means t is greater than 0. For the middle one, the only thing that this middle term can't be is 2. So I'm just saying t is not equal to 2. And then for e to the 2t, all real numbers apply. So that's what that r represents, all real numbers. So in fact, all real numbers won't affect the domain. So essentially it's, if they were all, if it was real, then it'd be all real numbers. But I kind of drew all pieces. I graphed it out, and then you can kind of look, and from there you can see what's common. So here's the first one. I've got a whole, or I could have used, whole or parentheses to do it, whatever, you're comfortable with. Some algebra books we used to use whole. Sometimes now they use parentheses a lot. Whatever, that's not too important. So this represents greater than 0. Whole at 0 going that way. The next one is not equal to 2. So there's just a whole at 2, and then 2 arrows going left and right to represent all real numbers. And then the last one is just all real numbers. So essentially what we're looking for then is the common between the first two. Like I said, whatever is common between the first two is certainly going to be part of the third one. So the real number ones, you kind of, if they're all real numbers, you kind of ignore that. So you see there's a whole at 0 and a whole at 2. So that puts us between 0 and 2 without touching 0 or 2. And then it picks up again on the other side of 2, then all the graphs go to infinity. Now, I'm not picky on how you write this answer. This is interval notation. This is fine. This is saying that interval notation, that 0 to 2 without including either one of those. And then 2 to infinity. And or written like this is perfectly fine. 0 to 2 and t greater than 2. So that would be the domain. That means for that vector valued function, you cannot put in any value for t that's not within this domain. It's basically an error. You have undefined points. Let's look at this next one. Square root of 4 minus t, and then sine of t, and then 3 over t. Okay, now be careful with this one. This is a little bit different, obviously, than if it was t minus 4. For 4 minus t, actually anything less than or equal to 4 would be okay. If it was t minus 4, the arrow would go the other way. And you can check that real quick. Let's put 0 in there and see if 0 better work according to this. So 4 minus 0, yeah, so square root of 4, that's good. So we definitely want, so negative numbers would work right here, no problem. The middle one, sine, all real numbers. You can put anything in there for either sine or cosine. And the last one, 3 over t, means t is not equal to 0. So I'm graphing these. So here's the first one. And I didn't even graph the real one this time. Like I said in the last example, you can kind of ignore the real valued function, real number ones. Because whatever you share between the other ones is going to be automatically part of the one that's a real number anyway. So, all right, here's less than or equal to 4 for that square root. Now here's all real numbers except 0. So you see now together, they connect at 4. They overlap exactly at 4, but they stop at 0 because of the bottom one. You can't include 0, and then all the way over to from the other side of 0 to negative infinity. So, reading it from left to right, like you would in interval notation, you would have negative infinity to 0 parentheses, because you're not touching 0, union with parentheses for the same reason, 0, but square bracket at 4, because it can equal 4 exactly. And then here it is written in inequality notation. T less than 0 or 0 less than t less than or equal to 4. So there's the process for finding domain of a vector valued function. Now limit of a vector valued function. Now here's something you got to kind of get used to here, is that, we're in anything you've done prior to this, limits have always been, real number answers if they existed. They're answers. But now this is going to be important to realize that the limit of a vector valued function is going to be a vector. The answer is going to be a vector. And whether it's plane or space. So you see the only difference between plane and space, it has that k there. So what you do is you evaluate each individual limit, and then that they go with I, j, k, or you can write them in component form. Now, if any one part of this does not exist, the the whole thing does not exist. But let's say you do one that's a space when you do 3 components. Let's say, the first limit's 2, the second one's 2, and the third one's 2. The answer is not 2 plus 2 plus 2 equals 6. The answer would be 2i plus 2j plus 2k, or, component form, you could write it as 2, 2, 2. Very important to realize that these answers are vector answers. And we got Stewie telling us here, so that's important when he tells us. Let's take a look at this one. Just working with them individually. Now, the first one and the third one are easy because you put 0 in there. Obviously, the first thing you want to do is plug a number in there, and if it works, then you're done. So e to the 0 is 1. E to the negative 0 is 1. But remember, from back in Cal 2, or you might have learned this in Cal 1, wherever you learned it, L'Hopital's rule and the indeterminate forms. You put that in there, you get 0 divided by 0. That does not automatically make that term 0 by any means. You have to, now in Cal 1, when I taught Cal 2, it may change down the road. We did L'Hopital's rule in Cal 2, but we covered this limit in Cal 1, and we learned that it was 1. But L'Hopital's rule shows that it's 1 also, real quickly and easily. You could do this by a table of values or whatever, but L'Hopital's rule, the derivative of the top over the derivative of the bottom, you'll get 1. But that was defined in Cal 1 as 1. So anyway, that limit's 1. So you see the answer is, each term is 1, so it's not 1 plus 1 plus 1 equals 3. It's either whichever form, it's either 1i plus 1j plus 1k, or in component form with the angled bracket, 1, 1, 1. All right. Let's take a look at another example. All right, this one, let's look at this limit. I won't read that out there, but you put 1 in there, that's going to work. Now you put 1 in here, you're going to get 0 over 0. Now 0 over 0 doesn't guarantee the limit will exist, but it guarantees that it has a chance to exist. It's when you get non-0 over 0 where it's game over. So this one actually, you do a L'Hopital's rule and you do get a limit here. So the derivative of 1 over ln of t is 1 over t. T squared minus 1 is 2t. And that gives you 1/2. But here's a problem. When you put 1 into there, you get 1 over 0. There is no L'Hopital's rule that will save you from that because that's not an indeterminate form. 1 over 0, game over. So that term does not exist. The limit of that term does not exist. That means the entire thing does not exist. Now here's one where it's approaching infinity. E to the negative t, that's just basically e to the negative infinity, which is essentially 1 over infinity, so that's going to go to 0. The middle one's obviously going to go to 0, 1 over infinity. And the third one, once again, larger power on bottom than top guarantees 0. But you see, the answer is not the number 0. So if you were picking answer choices in a multiple choice format and you saw one of them that had the number 0 and one of them that had this vector 0, 0, 0, you need to be choosing the vector answer 0, 0, 0. Okay. Continuity of a vector valued function. Basically, sort of like the domain idea. Just anywhere where it's going to be continuous, it's almost just like that. So, essentially you're finding its domain. That means that's where it'll be continuous. So same idea. So we got a square root of t and a square root of t minus 1. So we have t greater than or equal to 0, t greater than or equal to 1. I didn't even draw these out. But obviously they both would start at 1. You can't use anything between 0 and 1 because it would not work here. So that function is going to be continuous from 1 to infinity. And then for 72, first term, all real numbers. Second term, all real numbers, but the last one is going to affect it. So you can only take the natural log of positive numbers. So see, square root, you can say, because you can have the square root of 0. So t greater than or equal to 1 is okay. But here it's got to be t strictly greater than 1. So that would be your where it's continuous for number 72 here for this example. And we'll be dealing more with this later. If you saw this in Cal 2, hopefully, or if not, you can go back at whatever book you have. You can go back and look at parametric equations if you need a refresher. I think I have some Cal 2 notes. If not, I can put some in my whatchamacallit, new learning system, bright daylight, whatever it's called. I might have my Cal 2 notes in there, and you can look at it there. I haven't produced a video for it as of the time I'm doing this, but there may be a video at some point. You watch that too. But anyway, so what you want to do to do this is you want to take the more complicated side, and that's the one you want to put t in there. Sometimes there's 2 correct ways to do it, but one thing you wouldn't want to do here is you would not want to solve for x squared, because you don't want anything that would be like a plus and minus root. It needs to have one unique solution. So here, if you let x equals t, that means y would equal 4 minus t squared. So therefore, your vector valued function of this plane curve can be written as t comma 4 minus t squared. So that's how you'd write a vector valued function representing this equation right here. Now it says there are many correct answers. Should say there are possibly many correct answers. I can't really think of another good one on this one besides this one here, but anyway. Now it's number 52. Anytime you've got something that's circular or ellipse, you have to use these substitutions right here. So you see I have x squared over a squared plus y squared over b squared. So you let x equals a cos t and y equals b sine t. And let's see. So the square root of 9 would be the a, here would be 3. And then the square root of 16 would be 4. So your vector valued function based on the parametric equations. So x equals 3 cos t, y equals 4 sine t. Those are called your parametric equations. But now when we write them like this, they are a vector valued function. Okay, now I'm going to grab, here's the first one where x equals t and y equals 4 minus t squared. Well, the original equation, y equals 4 minus x squared, we kind of knew it was going to be a parabola. Now, I didn't indicate what values I chose for t. It doesn't really, probably start at 0. No, I guess I didn't. I started at something like -2 or whatever. Yeah, -2. But, I could have started farther and would have drawn more of the. So this one, it's only going to draw based on what values of t you tell it. So this one, yeah, obviously the graph would have kept going had I started earlier, but I'm just drawing the arrows to represent what's called the orientation. That means this is the direction it's going as t increases. So I can put -2 in here, you get -2, 0. Put -1, you're going to get -1, and 4 minus 1 is 3, so it's up here. Put in 0, you get 0, 4. So you see it's going in a clockwise orientation here. Later on, that orientation will be important when we start doing some stuff with some work stuff and a few other things. The direction that force field's going, when your force is going, will make a difference. Well, anyway, I'm going to graph this other one here in real time. So let's go back and so there's so I already have it in parametric form. Cosine, and then I hit x. X will produce t. And y is 4 sine of t. Like so. And I'll go over to my window. And it's already set at 2 pi, which is good enough. Now, unlike the one that I showed you with the parabola, this one's being ellipse, it would just keep circling on top of itself. So it really wouldn't matter what I put in here. If I put in 2 pi, 4 pi, 6, it's not going to draw more graph. It's going to be an ellipse. That parabola, if I would have started with t equals, a farther negative number, it would have shown more of the graph. But I think this is good enough here. Let's see what this, I can always change it afterwards. So long as this completes the ellipse, we're okay. I'm going to change a couple of things. I'm going to go zoom standard, and then I'm going to go zoom square. Still looks a bit circular for my taste, but I guess probably already is squared, I guess. Oh, that's a little better. That makes it look a little more elliptical. So let me cut this out. And then I'll put the original I'll put the parametric equations in there so sometimes it puts things in locations where I don't want them. Okay. All right. There we go. Let's shrink that down a bit. And let me get the parametric equations in there. Sometimes I put the window in there when I'm doing a graph, but I'm not going to this time. I'm just going to go back to the y equals and just kind of so put this right in here and shrink that down, and then that now shows us what we actually graphed. Although you did see it live, but if somebody didn't, they were just looking at my notes, they didn't see this. Okay, there we go. All right, let's see what we have here. All right, represent the line segment from P to Q as a vector valued function and by a set of parametric equations, both. Which we learned how to do parametric equations from the section on lines and planes and space. So it doesn't really matter what you do, but it's just basically, all it's doing is just taking the parametric equations and just putting it in vector valued form. So it's really not two separate problems. So what did we learn before here? We learned that just take the second point minus the first point. That'll get your multiple of t. And you can go either direction, P to Q or Q to P. That's still correct. 7 minus 2 is 5. Basically, we're getting our direction vector. Remember that term? 2 minus a minus 1 is 3, so that's our direction vector. So I'll start with P as my starting point, 0, 2, negative 1, plus 4t, 2 plus 5t, and then negative 1 plus 3t. So obviously I can get rid of the 0. And then here it is written in vector valued form. So that would actually be a line shooting up through space. And so there we go. That's not too bad. So it's just kind of taking something we've already done, and now we're writing it in a new format. Think about it. Let's see. Find r of t dot u of t. Is the result a vector valued function? Absolutely not. The dot product is scalar. So this dot product is not going to be a vector valued function. And so I've answered the question already before even doing the dot product. The dot product never represents a vector valued function, but a cross product between two vector valued functions would represent a vector. A cross product always yields a vector. So dot product, pretty easy here. So we've got 3 cos t, 4 sine t makes 12 cos t sine t. 2t times negative 6 cos t makes negative 12 sine t cos t. And then t minus 2 times t squared would yield t cubed minus 2t squared. So these two terms conveniently cancel, and that leaves me with t cubed minus 2t squared. And that concludes this video for vector valued functions.